Hello everyone, my name is Will Smith from the Chemical and Biological Engineering Department, and I'll be presenting on the production and purification of anhydrous sodium sulfide. Anhydrous sodium sulfide is emerging as a key chemical for the fabrication of sodium-ion batteries. It can serve as an active cathode material with a high charge capacity approaching 700 milliamp hours per gram, and it's also a key precursor for the synthesis of sulfide-based solid-state electrolytes, which possess high sodium ion conductivities on the order of 0.1 to 10 millisiemens per centimeter, and they may also enable the use of high-capacity sodium metal anodes. However, anhydrous sodium sulfide is currently fairly expensive, on the order of $10 per gram from Sigma-Aldrich, and has relatively low purity around 95%, with the primary impurities consisting of sodium polysulfides, as well as sodium oxysulfur compounds such as sodium sulfate and sodium sulfite. High cost and low purity of currently available sodium sulfide reflects the conventional synthesis methods, the primary one being carbothermic reduction of sodium sulfate. This reaction is conducted at high temperatures over relatively long reaction times and directly emits the greenhouse gas CO2. Material obtained from this process is typically fairly low purity due to oxidation during the reaction, as well as incomplete conversion of the sodium sulfate precursor. The second route, which is more preferred for research applications, is the dehydration of sodium sulfide nonahydrate, which is obtained via recrystallization of an aqueous solution of sodium sulfide. The nonahydrate is available in nominally higher purities, around 98%. However, when accounting for the excess mass of water, the anhydride is very likely only around 95% pure. And in addition to this, the recrystallization process is fairly costly and time-consuming, and it results in a hydrate that is only really 32% sodium sulfide by mass. There's a third route to a so-called technical-grade sodium sulfide hydrate, which is produced as a byproduct of a couple industrial processes, primarily the caustic scrubbing of sour gases with a sodium hydroxide solution. And this material is relatively inexpensive, about 10 cents per gram from Sigma-Aldrich, and has a higher concentration of sodium sulfide than the nonahydrate. However, its purity is typically inferior to that of routes 1 and 2. So the research aims that I'll be presenting on today are twofold. First, I'll be presenting on the purification of low-cost technical-grade sodium sulfide hydrate. And second, I'll be presenting on a novel direct synthesis of sodium sulfide using a liquid phase synthesis approach. The sodium sulfide hydrate purification process is outlined on this slide, with an image of the as-received sodium sulfide hydrate shown here on the left. After grinding this material to reduce the particle size, it can be thermally dehydrated at 70 to 150 degrees Celsius under reduced pressure to produce an anhydrous technical grade sodium sulfide. This material can then be purified further by reacting with hydrogen gas at 400 degrees Celsius. And in the process, the hydrogen reacts with the solid oxygen and sulfur species to form H2O and H2S gases, which self-separate from the reactor bed. The result is a high purity form of anhydrous sodium sulfide, and you can note the stark contrast between the initial and final product. Historically, this purification process has been conducted around 900 degrees Celsius with reaction times around 12 hours. However, for the first time, we've demonstrated that with optimized reactor design, this purification can instead be conducted at 400 degrees Celsius with reaction times on the order of 7 hours. In addition to this, we also showed that the reaction kinetics were well fit by a shrinking reacting core model with strong internal mass transfer limitations. And the result of this process was nearly complete abatement of the oxysulfur and polysulfide species. And the purity is nicely represented by the color change of the material from a bright yellow to nearly pure white. On the other hand, the liquid phase synthesis is outlined here. The process consists of first dissolving sodium metal in an alcohol to produce a sodium alkoxide precursor solution and producing hydrogen gas in the process. Next, the sodium alkoxide solution is contacted with hydrogen sulfide gas, during which the hydrogen sulfide is completely consumed, reacting with the sodium alkoxide to form a sodium sulfide solution and regenerating the original alcohol. Afterwards, the anhydrous sodium sulfide is easily recovered via solvent distillation at moderate temperatures. And overall, the net reaction is between sodium and H2S, with a key benefit being the recovery of the valuable hydrogen stored in the H2S gas. We investigated a couple different alcohols for the synthesis, the first being ethanol. However, we found that the synthesis in the ethanol solvent was fairly sensitive to H2S stoichiometry, with 100% of H2S resulting in formation of sodium hydrosulfide byproducts, whereas 92% addition of H2S resulted in residual sodium methoxide crystallizing in the sodium sulfide product, with 95% of the stoichiometric being found to be the optimal stoichiometry, resulting in nominally phase-pure sodium sulfide. However, using the methanol system was found to be much less sensitive to these parameters, resulting in higher crystallinity and higher purity material with 100% addition of H2S, and with an added benefit of a lower thermal budget due to the higher volatility of methanol compared to ethanol. So to put everything together, we compared the hydrogen reduced and the synthesized materials to 2 commercial samples from either alpha azar or sigma aldrich, using a complementary suite of characterization techniques including TGA, FTIR, XRD, and Raman. And we found that FTIR and Raman were the key characterization techniques since they can easily detect the presence of oxysulfur and sodium polysulfide species respectively. And we found that the reduced and synthesized materials were at least comparable to, if not superior to, both the commercial samples in all characterization techniques that were used. So in conclusion, today I've presented on 2 routes to producing high purity battery grade sodium sulfide. The first being the purification of low cost technical grade sodium sulfide hydrate by first dehydrating the material and then reacting with hydrogen at 400 degrees in order to remove oxysulfur and polysulfide species, with the kinetics of this reaction being characterized for the first time. We also presented on the novel synthesis of anhydrous sodium sulfide in an alcohol solution at ambient temperature and pressure, with methanol being preferred to ethanol. And finally, we compared samples produced through either route to currently available commercial samples of sodium sulfide and showed that they are comparable to, if not superior to, both of them, not only in terms of purity, but also in terms of cost, as shown here on the right. We expect that the materials cost of either the hydrogen reduction or the synthesis process is 1 to 2 orders of magnitude cheaper than the currently available forms. And this work was recently published in the Journal of Sulfur Chemistry and can be found at this citation below for more details. So to finish up, I'd like to thank my advisor, Dr. Colin Walden, as well as my group members, Jerry and Saeed. And I'd like to call out Jerry, who is an undergrad researcher who developed the liquid phase synthesis approach. And of course, thank you to the funding sources, NSF and CoEdit. And thank you for your time.